before we dive into the problems, feel free to ask any questions if you have any during the review. So first one, power balancing. Okay, if I draw a circuit for you guys like this, like voltage source, another resistor, would you be able to tell me I'm just creating a problem randomly? 5 ohms. Let me see. 2 ohms. Yeah, but there's a very similar problem on the finals, okay? So just showing you a circuit like this, very simple DC circuit. Can I just directly randomly create the voltage source over here for you guys? Or is being restricted by something? Or being limited by something? Like 2 volts, will that work? That's a very good thing, very good problem to think about. How do you verify? What's the limitation here? The current source. Because the current source is going to force the circuit to be exactly 1 amp. Okay? And now let's see if this works, okay? I don't know yet, I just randomly created. So what's the voltage drop across this guy? 5 volts. Okay? What about here? 2 volts. Voltage-wise, would it work? Voltage-wise is probably fine because we don't know the voltage here. So since you know the voltage over here, which is 2 volts, let's see. What's the voltage if I label here plus minus like this? So we got 2 volts here. How do we calculate it? You got 2 volts here, okay, and dropped by 2 volts. So what's the voltage here? 0 volts. And being boosted by 5 volts, you're getting 5 volts over here, okay? So which is fine. You got 5 volts for the current source. Doesn't matter. Nobody cares about the voltage across the current source, right? But however, if the total power consumption getting balanced, because the total power delivered power and absorbed power should be equal, right? Absolute value should be equal. Let's find out. Is this guy absorbing, right? 2 watts absorbing? What about this guy? Delivering, because it's flowing out of the anode. This guy absorbing 5 watts. How about this guy? Shooting out from the anode. So it's delivering 5 watts, right? So it's balanced. Okay, it's balanced. If there's a circuit problem similar to this one, you should be able to calculate if this is balanced or not, okay? It's very interesting. If I put a resistor here, it's getting balanced. If I don't put a resistor, nothing is actually absorbing, absolutely absorbing. It may be limited. Let's think about this on Wednesday, see if I can create another example for you guys, all right? But for this one, it's solved, okay? It's balanced, and absorbed power equals the delivered power of the circuit, and you should know how to calculate the absorbed and delivered power for each component. Okay? Another fundamental problem from the earlier of the semester is, regarding KCL and current divider and voltage dividers. So how to derive the equation of the current divider? Very simple, right? I is R1, R2, I1, I2, and I started using the conclusion for the rest of the semester, but when we try to derive I1 and I2, it's basically using the common voltage for all these shared nodes. Remember? The reason we can apply current divider theory for this kind of circuit is because they have the shared common voltage on the top, or the voltage drop across the two terminals. So I1, the first step is you just have to find out the voltage over here first, okay? So which is V I times what? The combination of the parallel resistor, which is R1, R2, over R1 plus R2, okay? That's the voltage across these two terminals. So if you want to find out the current flowing through R1, you just have to divide the whole thing by R1. That's why you leave a R2 on the top. That's why when we are trying to write down the current divider equation, if we want to know the current flowing through R1, we put R2 on the top. Okay, that's why we did it that way. Okay, so you want to directly apply this kind of conclusion to make your calculation faster, a bit faster. Okay, and for the voltage divider series, a bit easier. Okay, you got R1, R2, V out. This is source voltage, Vs. So you want to calculate the current first, which is Vs over R1 plus R2, and times the resistor over here, which is R2, to find out V out. So that's why it's forming a voltage divider equation, which is V out equals R2 over R1 plus R2 times times the source voltage. Okay, some basics. And for KCL, I know a lot of people already know what KCL is, right? So all the current flowing into the node, the summation of the current flowing into the node is 0. Okay? So if you have a different circuit topology like this, you should know that KCL also applies to this type of circuit. 1, 2, 3, 4 currents, like the main currents over here. This is this is I1, I2, I3, I4. It's just one node. It's one piece of metal. You can melt it and merge it to one node. So this is just the 4 branch currents. This is the total current. Okay? Same concept. No matter how I draw the circuit, okay, it could be this. Okay, it doesn't matter how I draw it. If I'm treating this guy as one node, it's just one node. It's the main current and getting split into these branches. You can apply KCL to this kind of topology as well, right? Any question by far? Some fundamentals from earlier of this semester. Okay. Starting from, I think, homework 8. Just getting to the nonlinear domain. So from homework 8, you want to look into the problems like natural response, step response, I think one cheat sheet is allowed for the final exam. So you can put these equations onto the cheat sheet. For example, VC T equals, for step response, VCT, which is a capacitor voltage, equals VC infinite plus VC 0 minus VC infinite times e to the minus t over tau. So tau is a time constant for RC circuit. It's just R times C, right? So we got two different cases, two different special cases. If it's a natural response, for example, it's just a discharging through a resistor. There's a VC0 here at the very beginning, and just discharging over R. Okay, you can still apply this equation, but it's just a special case. The special case of the step response. It's something you guys need to know, okay? How do we find that out? So for this one, whenever you discharge from the capacitor through the resistor, what's the final voltage of across the capacitor? 0, right? There won't be anything, it's just gonna totally discharge. So eventually this becomes 0, and VCT equals what? VC0 times e to the minus t over the time constant. And this becomes what? Natural response. Okay? Starts from the same equation. So what if you have a circuit like this? Actually, you don't. If you have a switch, you don't need this anymore, right? It's just a DC voltage, like 5 volts. You close the switch at T0. This is definitely the forced response. But it's given that VC0, 0 volts. There's no original or initial voltage across the cap. You can still use this equation. However, the initial voltage becomes 0, right? So VCT equals VC infinite minus VC infinite, which is VC infinite times 1 minus E minus T over tau, right? This is definitely a forced or step response or forced response. No question on that. No question on that. Because it's trying to force the voltage across the capacitor to be this source voltage. So eventually this becomes 5 volts. So which one is the 5 volts over here? Yeah, this is 5 volts, right? So if let me find a circuit so we can analyze that type of circuit by looking at the Sabin's equivalent over there. Just in case you guys are not super familiar with that. Okay, for example, this guy. When switch is open. So originally, when switch is closed, it's charging up this inductor, and eventually this becomes a conductor over time after 100 years. Okay, so it's just a wire. It's shorting this circuit, but you still have a current, becomes the initial current across this inductor. If you open the switch, okay, so this is gone. So this is going to discharge across this resistor. Okay, that's a natural response. Okay, I believe people who have been attending classes should be very familiar with this type of circuit. Make sure you can do this. Okay, it's definitely will be on the final. Natural response, discharge through inductor or capacitor through a resistor. It could be a very simple circuit, just a one resistor, or it could be a Sabin's equivalent circuit you have to find out from a resistor network. Let's see. What about this one? Okay, so time 0 is getting closed. So before time 0 is open, so it's charging up this guy, and this becomes a wire because the current flows through this guy. Okay, so whenever this is closed, what's happening? This will discharge across the rest of the circuit. Okay, so you have to look backwards to find out the equivalent R, so you can find out the tau, the time constant, right? Okay. This will be one problem on the final. Let's see. Okay. What about the homework 11 problems? Without the Y connected three-phase voltages, it won't go too deep into the tutorial problems, but fundamentals only. Okay. So, for example, A, B, C, all right, three phases, 120, 120, 120. So it's positive or negative sequence? It's positive because it's clockwise, ABC. Okay, so it's positive. It's a positive phase sequence. Okay, and if the three voltages are given as VA, I'll just show you. Okay, VA is 339 cosine 377 TB. VB is 339 cosine . So it's going to ask you if this is balanced. So you are looking at amplitude and frequency, okay, and also the 120 degrees apart. So it's basically looking at amplitude, frequency, and it's 120 degrees apart. Okay. So it's going to ask you if it's balanced or not, and ask you to explain why this is balanced. So want to tell they have the same amplitude, the same frequency, and they are 120 degrees apart. That's it. Make sense? Okay. So what a negative phase sequence looks like? Yeah, it will be ABC. If you follow the ABC sequence, it's going to be counterclockwise, right? So it becomes A, B, C, like this. All right. It's going to label the voltage as VA, VB, or VCs. So you don't have to worry about that. Just look at ABC. If the ABC sequence is clockwise or counterclockwise, so you can tell if it's positive phase sequence or negative phase sequence. Any questions on this? Easy by far. 50 points already. Right. What else? Let's see. This one. Okay, this is done. Homework 10. Let's see. Homework 10. This is 8. Oh. transformers, you need to know a conclusion, which is the coil number of turns of the winding. For example, is 1 versus n. Okay, so these numbers are the number of turns of the winding, and this is the primary winding, of the coil, and this is the secondary winding of the coil. If I label the voltage here as V1, remember it's not here, this is Vs, this is source voltage. I label here the node right before the primary winding as V1, and label current here as I1. Okay? And then you have a conclusion like this. Probably it's better to use N1 versus N2. I'm sorry, N1 versus N2. It's more general, okay? N1 versus N2. So then you know that V1 over N1 equals V2 over N2. And I1 N1 equals I2 N2. Both absolute values. So know that V1 equals V2 N1 over N2. And you know that I1 equals I2 N2 over N1. So why do we want to find out V1 and I1? V1 and I1 because we can use V1 over I1 to find out the impedance, equivalent impedance of the load. The problem is it's not directly electrically connected. It's using magnetic field to do the indirect connection between the source and load. But the thing is, you have to find out a equivalent impedance of the load here. It looks weird because it's not directly connected. You can use Ohm's law to find out the impedance. However, you can use this equation to calculate the equivalent impedance of the load. It is a load, right? It's transfer energy using magnetic field indirectly, but it's still a load. It's still a load to the source. It's not directly drawing current from the source, but indirectly drawing energy from the source through that magnetic field in between the coils. So we should be able to find out the equivalent impedance from here by using V1 over I1. Okay, so what is V1 over I1? And now we know V1 and I1 already. So just directly use V1 over I1. That is going to give you V2 over I2 times, if you do a division, you can find out this equals N1 over N2 square. Okay, let's add an impedance over here. ZL. So impedance of this load is ZL. But the thing is, when you are looking into V1, into the primary, the equivalent load of the everything behind this line wouldn't be ZL. It's going to be this. Sorry. So you can find out this V2 over I2, V2 voltage, I2 current. V2 over I2 is basically ZL. So this equals ZL times N1, N2 squared. So the equivalent impedance, if you don't have the coils over here, it's going to be ZL, but now you have a coil, it becomes ZL times N1 over N2 squared. Okay? So this is a conclusion you need to know. What's that?
Would we normally be like finding ZL then in that?
ZL is usually given.
Would we find it?
Oh yes, sometimes yes. So for example, if I give an R here like 5 ohms, okay? So it's gonna ask you to find a ZL to maximize power delivery to the load. Because the load is over here, it's everything over here is the load, right? Not just the ZL, it's including this part as well. So the maximum power delivered to the load will be have to be like this part equal to 5 ohms, right? Does that make sense? Let me come back, getting slower a little bit. So here's the source voltage. Remember previously we have a conclusion that if we have a circuit like this, sometimes we convert everything to a 7th equivalent, for example, just to make it more general. So choose RL to maximize the power delivered to the load. So usually we have RL equals RTH. So it's basically you have your RL equals whatever resistor over here of the equivalent circuit. That's a conclusion we can directly use. Okay. So if this and this they are equal, it's maximizing the power delivered to the load. Keep that in mind. Same thing over here. So look at this one. It's a source, it's a resistor, and that's a load. That's a huge load. ZL prime, for example. The whole thing is ZL prime. Okay, so it's a very similar circuit like this one. And you got a resistor over here, and that's the load. How to maximize the power delivered to the load. Okay, so you just have to make this load equal to 5 ohms. So the problem could be find out the ratio of the number of turns of the coil to maximize the power delivered to the load. Because we know either one probably is given. Okay? ZL is given, then you find out N1 over N2, the ratio. Or N1, N2 is given, you find out ZL. Because this is V1 over I1, which is the equivalent impedance or resistance behind this line, okay? Or after this resistor. Does that make sense? You just need to make this guy equal 5 ohms. Okay, depending on the problem, you are either calculating ZL or calculating the ratio here. Any question on this? That far? No? Okay. Let's look at one of the average power problems. It could be homework 10, 10.7. But before we do anything, we need to be clear on one thing. So if I have a capacitor, got a voltage drop and current flows through it, okay, is the current leading or lagging the voltage? Which one? Yeah, so after the end of semester, you should answer this question in 1 second. Let me go through this one more time with you guys. Why? It's leading, okay? So capacitive circuit is leading, current is leading the circuit, leading the voltage. Why? It's really easy to find out actually. So V, let's assume that V is 0 degrees as a reference of the phase angle, okay? And usually the impedance of the capacitor is negative, right? It's usually like negative AJ. A is just a constant. It's negative something J. Voltage is the zero degrees phase angle as a reference, and impedance of the capacitor is usually negative something J, and you add a real number 0 in front of it, right? It's basically negative 90 degrees. Do you agree with that? Everyone should know this by this time, okay? So this is negative AJ. So it's negative 90 degrees. So this becomes V 0 degrees over A, negative 90 degrees. And this is V over A as the amplitude. And the angle is 90 degrees. So this is which parameter is the angle, 90 degrees. Whose angle, which one's angle is 90 degrees over here? Current. Since we use voltage divided by impedance, we're trying to get a current. So the current becomes 90 degrees. So the voltage is what? 0 degrees. So it's basically, if you got a voltage here, and the current is over here for the capacitive circuit. So for a capacitive circuit, current is always leading, right? Current is always leading. And if you write down the equation for power factor of this circuit, just one capacitor anyway, of the circuit, it's power factor cosine theta v minus theta I, right? So this one becomes a positive number. Wait, is that positive or negative number? Because current is 90 degrees and this is 0 degrees. Although you are still getting a positive power factor, but the thing is, whenever the angle here inside the cosine function becomes negative, it's called a lagging or a leading power factor. The leading power factor. So the conclusion here is, if it's a capacitive circuit, okay, so current must be leading. If the current is leading, it's giving you a leading power factor just by definition. Okay? So if the current, keep in mind, if current is leading the voltage, then we are getting a leading power factor. One of the questions on the final, okay, is asking you if it's a leading power factor or lagging power factor. How do you find out if it's leading or lagging? I mean, we're not talking about the current. We're talking about the power factor. How do we find out if the power factor is leading or lagging? Angle here inside. Or you just find out if current is leading or lagging, right? If current is leading, power factor is leading. If current is lagging, power factor is lagging. What about the inductive circuit? For inductive circuit, lagging, so current is lagging, so it's a lagging power factor. Make sense? Okay, this is something you must know. Okay. Capacitive circuit, current is leading. Inductive circuit, current is lagging. This VL 0 degrees over AJ, which is VL 0 degrees over A, 90 degrees. So this becomes VL over A and negative 90 degrees. So which means if you have a voltage as a reference at 0 degrees, and then your current is at negative 90 degrees with the amplitude of VL over A. Okay, so it's basically your current is lagging. This current is lagging in the inductive circuit, so power factor is lagging as well. Just by definition. So let's calculate average and reactive power for the following 3 circuits. We probably can finish maybe all of them. Let's see. Example 1. Ten J. Keep in mind, first thing when you are working on problems, I'll probably repeat this on Wednesday as well. So first thing, you have to convert all these parameters into this phasor form. It's giving students partial credits. Keep that in mind. So first thing first, what to do for this guy? What is this in phasor? 20 and 0 degrees, right? Do that first. So this might be something else, like 20 millihenry or something. So first thing, convert it to something J. Partial credits, do that first. So it's gonna ask you average power, reactive power, power factor, lagging or leading, what's the first step for this type of problem? There are several problems that are very similar. I'll ask you probably 2 of them, asking you to calculate average power, reactive power, power factor, lagging, leading, things like that. So what's the first step? What's the component consuming average power? Resistor. Resistor is the only component consuming average power. And what's the equation for average power? P equals what? Vm times Im over 2 cosine theta V minus theta I, right? That's the equation to calculate it. Keep in mind, this is the peak voltage. If the problem description tells you that this is a peak voltage, it's a peak voltage. So you just have to directly insert that value to Vm over here. So this is Vm. They are the same thing. Why? Because VRMS is Vm over square root of 2, right? And IRMS is Im, the peak current, divided by square root of 2 as well. So they are the same equations. So it's given that this is the peak voltage, 20 volts. So it should replace Vm over here for the first equation. So how to calculate it though? Equals what? So we only care about the resistor. Remember, I introduced 2 different methods. You either focus on the entire circuit, entire impedance, or you just focus on the components that consumes average power. I think that's the easier way to do it. Let's just do that first. We'll go through the other method probably on Wednesday. So average power and resistor is the only component consume average power. So we can just look at the resistor. It's going to be fine. Don't worry about that. So ignore this guy for now. What's the voltage across it? Peak voltage, 20 volts. Vm, right? What is Im? Yeah, it's going to be 20 over 10. Divided by 2. And cosine theta V minus theta I. So what's the the voltage and current phase difference over the resistor? What's the difference of V and I angle difference? 0. There's no angle difference, no phase shift for the resistor itself. So it becomes 1. So it's just basically 20 times 20 over 10 over 2. It's 20 what for average power? Watts. What is Q? For Q, you focus on the inductive component only. Okay, same voltage, but equation becomes Vm Im over 2 cosine theta V minus theta I, and which is 20 times. So when you are converting voltage between voltage and currents, keep in mind you always use the amplitude, all right? So for this guy, this is basically 0 plus 10J. So the amplitude is just 10, right? Just 10. Still 10, okay? Still 10. So I am, for this part, for this guy, is going to be 20 over 10 as well. Divided by 2, and sine theta v minus theta I instead of cosine, okay? Sorry, sine. So V and I difference for the inductor is 90 degrees. So sine 90 degrees is 1. So this is basically, eventually the reactive power of the circuit is 20 as well, but what's a unit for reactive power? It's VAR, right? VAR. Okay? So what's the apparent power? Apparent power equals P squared plus Q squared square root. Eventually still 20. But what's the unit? Volts ampere. It's VA. What's the power factor? P over S. (20 over 20). It's 1. So efficient. And then is this leading or lagging? Leading or lagging? It's an inductive circuit, right? It's an inductive circuit, so it's definitely leading. Lagging, sorry, lagging. So it's going to be a lagging power factor. So if you, it's an inductive circuit, right? So it's lagging. But if you want to verify it, you can also find out if the current, you can also calculate the current, the complex current, and compare with the 0 degrees of the voltage. See if the current is leading or lagging. If the current is leading, then the power factor is leading. If the current is lagging, the power factor is lagging. Either way, okay, but I can directly tell it's definitely lagging, but you can verify it by using this divided by the complex, the impedance, and find out the complex current as well. Okay? Do you want to verify it? Let's see. So what's the overall impedance? Z equals what? 10 in parallel with 10J, okay? Which is 10 times 10J over 10 plus 10J. That's the overall impedance, right? So current equals, so I already drew the conclusion here, but let's find out. So current is V 0 degrees, 0 degrees over here, divided by 5 plus 5J. Okay, so which is V over 5, 0 degrees, 1 plus J. Okay? And this is V over 5, 0 degrees over 1. What's the degree here? What's the angle? 1, 1, 1, 1. What's the angle? 1, 1. What's the angle? 1, 1. What's the angle? 45. So this becomes V over 5 current, lagging. Okay? It's the lagging power factor. Any question on this? Good so far? So if I So on Wednesday, we'll go through more problems on this type of question. But for example, adding more components to it, like this. So let's do this. I mean, if you have time, work on these problems, and we'll go through this on Wednesday. Okay, so it's better like you work on it first.